Hey, how's it going? We are going to go over intro to limiting and excess reactants. We've needed to understand mole to mole, gram to mole, stoichiometry. We've had to understand balancing chemical equations. We needed to even understand the periodic table, what's in the periodic table, and what do we do with charges to even get to balancing a chemical equation, and so much more. But we're here now, and I'm going to go over these notes in order to help us derive where these definitions come from and integrate them into our plan. So I'm going to start this off. We're going to look at some definitions here. We have reactants. A lot of what we've been doing is doing an A plus B, or like this plus this will react. And it's going to make some form of a product, typically containing A and B. We know that we utilize the conservation of matter. So everything that is in A and B will come out in this A and B, will come out in this A and B product. If it doesn't prove that, then it's most likely not scientifically sound. Like if we have aluminum on our reaction over here, and we don't have aluminum over here rather. And so that doesn't make any sense. Like, where did it go? What did we do with it? Maybe there was something that occurred in our reaction process, but we want to stay sound with that. So just catching us up to speed, going rather quick with that. So limiting reactions, these are reactants or chemicals that limit the reaction. So let's see here. I won't try and erase it this time. Chemicals that limit the reaction. And then we also have these excess reactants, and this is anything left over after our reaction stops. Okay, so what this is kind of saying is that if I have, let's say I'm baking something and I need 3 eggs for the pound of flour that I have. And I know that's not a very realistic example, but let's say you need 3 eggs with this pound of flour to make bread. Horrible analogy, but let's just say that's exactly what you needed. Well, let's say I only gave you 2 eggs. Well, you can now only make 2/3 the amount of that product. You cannot make the whole product any longer. You're going to have an excess amount of flour if you only have 2 eggs. It won't utilize that flour. If that recipe is sound, which this is a theoretical recipe that I factually know isn't actually how you make bread, but let's say it was. The 2 eggs are not sufficient enough for this theoretical recipe. You would only be able to make 2/3 of that. And that's pretty neat because we have 3 eggs. Now we only have 2 eggs. That's 2 of the 3. We only can make 2/3 of the product. The result with chemistry works the same. So we're going to look through this. So we are going to use the following recipe for ham and cheese sandwich: 2 pieces of bread, 3 slices of ham, and 1 slice of cheese. Okay, great. We have some rules. That's the recipe, the theoretical recipe or the factual recipe, whatever. If you have 14 slices of bread, 12 slices of ham, and 20 slices of cheese, how many sandwiches could you make before you run out of ingredients? Okay, let's write this all out, and I kind of have a cheat sheet over here to rock this out. So we have some 14 breads here as listed right here. Okay. We have 12 slices of ham, 12 ham, and we have 20 cheese. 20 cheese. Okay. With my cheat sheet, we can no. So let's think about how we make a sandwich. With 14 breads or slices of bread, we want one on the bottom and one on the top. That's typically how we make our sandwich. So we have our little bread slices here. We need 2. That is a terrible bread, but that's what we're going to use. So we have 2 of them. So that means we can only make 7 sandwiches with these 2 breads. Now we have 12 hams. Okay, 12 hams. And what our formula here is that it requires 3 slices of ham. So if we have 3 slices of ham, and we're only given 12, well, 12 divided by 3 is 4. So we can only make 4 sandwiches, and this is the product, is these sandwiches. Now let's look at the cheese. Well, we only need 1 slice of cheese. So this is just, I'm not going to write out all that, but let's just say 1. So 1 cheese, so we can actually make 20 sandies with, only needing 1, and we have 20. Okay, so looking at this, we clearly cannot use all the cheese. We can't use all the cheese. We can't use all the bread. Why? Because of this ham. This ham here is totally limiting what we can do with all of our ingredients. If I was a business owner, and let's say I don't care what sandwich shop you have, but I said you need to make these sandwiches with 2 slices of bread, 3 slices of ham, 1 slice of cheese, and that's what the customer is buying, then that is what you make. If you go to the grocery store and you're so used to buying a specific product that has the exact type of ingredients, you don't want to mess with the customer, or else they'll notice that deficiency or a change without you saying, and be like, I don't trust this business anymore. So it is a crucial idea, even if you aren't a chemist, to understand what limiting reactions are just based on that. You want to stay true to your recipe. Okay, what will you run out of first when making sandwiches? Okay, well, we just said that. Ham, right? We're going to run out of ham. Okay, there's no doubt about it. And what 2 ingredients are left over? Well, we got a ton of bread, and we got a absolute ton of cheese. Okay, maybe you can make a massive pizza, bake a bunch of that cheese on that bread. Okay, awesome. But either which way, that is the, or rather, leftover of what we have. Let's move forward here. I got to move down my little cheat sheet to make sure I'm on par here. If you had 40 slices of bread, 62 slices of ham, and 40 pieces of cheese, how many sandwiches were you able to make? Okay, well, utilizing the same recipe, 3 hams, 1 cheese, 2 breads, we need to write that out. So we have 40 bread. We have 62 ham, and we have 40 cheese. Well, cheese is easy. Cheese is easy. We're gonna be able to make 4 sandies with that, right? 4 saddies. Okay. Ham, 62 divided by 3. It just so happens to be 20.6. We could calculate that, but I got my cheat sheet over here. 20 sands. Okay, and then we look at this bread, and we can actually make 20 sandwiches there. 20 sands. Sands will equal sandwiches. Okay. Just for the literal out there. Sandwiches and even saddies and sands. Okay. So the bread, we can only make 20. At least with the ham, we can get a little more and cut a little sandwich, 2/3 of a sandwich out roughly. And then with the cheese, we got a ton of cheese left. So what are we left with? What do we have in excess? Or rather, let's start here. What is our limiting? Well, it's our bread this time. It's our bread this time. Okay. Oh my goodness, I keep erasing. Here, let's just start this over here. Boom. Okay, it's our bread. Our bread is limiting us from being able to make more sandwiches to code. Okay, and now what are our excess reactants? Well, our ham will be in excess by a little bit, and our cheese. My handwriting gets off the lower I go on this little pad here. Okay, now we're going to do one more practice. I'm going to do one more here. If you had 30 slices of bread, 21 slices of ham, and 18 pieces of cheese, how many sandwiches were you able to make? Okay, let's look at this. 30 bread. Well, 30 divided by 2, because we need 2, so that's 15. We'll just write sands. Oh my goodness, I keep deleting. I'm going to move my hand here. 15 sandwiches, okay? And we have 21 hams. Okay, 21 hams. We have 7 sandwiches with that. 21 divided by 3. And then we need our cheeses. We have 18 cheese. Well, we can make 18 sands with that. Okay, so we're able to make a differential amount, a different amount for each ingredient that we have here based on how much of it we have. Well, clearly this ham is holding us back. We can only make 7 sandwiches with this ham. So we are limited due to our ham. Our ham is holding us back, leaving us with more bread and more cheese. Okay, putting this back into a business analogy, if you were limited, if you had a limiting, let's say you got a call from a contractor and the contractor said, we don't have enough of this, and that's part of your recipe for whatever you're making, and you have an excess amount, and that excess amount is going to go bad. Well, you're not just going to sit there and say, well, I guess we're going to throw it away. You're probably going to make a product, or you're probably going to try to figure out what you can do efficiently with those excess products. And I'm sure a lot of companies do that. You see a lot of non-name brand stuff coming from the same factory these days. I'm not confident, but I would theoretically assume that if they had an excess amount, they're not able to ship enough out. Well, let's just label it something else, pack it differently, and push it out. Why not? It makes sense if you're given even the same. Let's just say our company was only cheese. We had 100 cheeses, but we were only limited to sell 52. What are we going to do with that 48 left over? Well, let's repack it, reforge it. What are we going to do with it? So there's multiple different ways you can look at why limiting reactions are important here. All right, let's scroll down here. So we're going to use this 2 sodium plus chlorine or chlorine gas, Cl2, is going to react and produce 2 sodium chlorides or salts as we know it, or 2 moles of sodium chloride. And that's all listed right here. I'll kind of wiggle it in. Okay, you have 14 grams of sodium and 35 grams of chlorine gas to react in order to make sodium chloride or salt. Okay, one chemical will limit your reaction and the other will be left over. Left over after your reaction is done. So one is going to limit it and one is going to be left over. It's kind of the game we're playing right now. Okay, to figure out, I'll leave that right there. To figure out which is the limiting reactant and which is the excess reactant, we need to know how much sodium chloride or salt each reactant can produce. Okay, fine. So let's check out what this is asking of us. If you have 14 grams of sodium, and it looks like we have a stoich map here, 14 grams of sodium, how many grams of sodium chloride or salt can you produce? Okay, so our stoich map is pretty solid. We need to convert these grams. If we looked at our periodic table, which I don't know if I have one prepared, but on a periodic table, if you looked where sodium is, it would actually be 22.99 grams. And that is how many grams are in 1 mole of sodium, in which, because this is stoich, you'll notice that there's 1 mole right here. So we got to make sure that that is our denominator for that numerator of 1 mole. Now we need to do in this arrow, this middle box, is the ratio. So looking at our, where is it? Okay, we actually have to keep this up here. So I'm going to kind of put parentheses around this. Hopefully you're noticing me do that. That is our formula. 2Na plus Cl subscript 2 produces 2 coefficient or moles of sodium chloride. So our molar ratio right here, the moles of NaCl is actually 2 because of this 2 here. And I'm sure we remember that from our previous lessons. And our sodium, our mole of sodium, well, if we look right here, that's also 2. Okay, so we lucked out. They're both equal. And then the last part here is how many grams are in sodium chloride? Well, I have my little cheat sheet here, but if we looked on the periodic table and added these up, it would be 58.44 grams. And I just deleted it again. Okay, there we go. Okay, so if we did all of the multiplication and did this, I can actually show you a pretty neat thing here. If I type this in, or actually let's do it on my calculator. So use a calculator to rock this out. I do 14. We're just kind of following this pattern here. So we do 14. We don't need to do times 1. Well, we could. I'll say times 1 times 2 times 58.44. So we'll just start with that. 14 times 1. You don't have to, but I'll put it in just so you know. Times 2 times 58.44 equals, and I get 1636.32. I'm going to divide that, parentheses, 22.99 times 2. So I'm doing this bottom part now, 22.99 times 2. It's being divided by those two things. You can do times 1, but it doesn't really make sense. And on parentheses, press equal. I get 35.59 if we round up. 35.59. I rounded that one up. Okay. And then we are ending up with grams of NaCl. Okay. So we get that. So even though in 1 mole of sodium chloride, which you can notice right here where I'm putting all of these arrows, right? In 1 mole, we have 58.44. But because we were only given 14 grams of sodium, or Na, we produce less. Okay? We produce less of this. So we would require more sodium in order to produce more sodium chloride in this given reaction. Okay? Less than 1 mole, that is. Okay, let's look at this next one. All right. If you have 35 grams of chlorine gas, or Cl2, how many grams of sodium chloride can you produce? Okay, so if we look, we are already given the 35 grams. That's great. Of kind of write over stuff quite frequently. There we go. And in 1 mole of chlorine gas, how many grams are there? Well, we need to look at our periodic table. If we do, we find that chlorine's around 35, and 35 times 2, I think it's 35.45 or something like that. But if we do that times 2, my cheat sheet is indicative of 70.90. And so again, that's just 2 chlorines combined, chlorine gas. Now we look at our mole ratio here. NaCl and Cl2, I remember, so NaCl is right here. I'll draw even another arrow to this. There's 2 moles here, but Cl doesn't have any moles attached to it. Okay, there's nothing in front of it. That just means there's 1. So there's 2 NaCl, and there's 1 mole of Cl2, or chlorine gas. Now, grams, we figured this out in the last one, but if we looked at our periodic table and put sodium and chloride and added them together, rather, we would get 58.44 grams. And that is in 1 mole of sodium chloride. Let's do the math. We have 35. We're just doing the numeration on the top. Times 1, times 2, times 58.44. We get 4,090. So I'll just kind of write that. I'll wait. And we divide that by parentheses 70.9. Times 1. You don't need to do the times 1, but whatever. And unparentheses it. And we end up with 57.70. And that's going to be grams of NaCl. Okay, so we're recognizing that due to how many grams of chlorine we have been given, we are unable to make more than a mole of sodium chloride. In fact, it limits how much in 1 mole we have. So kind of cool. So in these 2, or it looks like we have A and B, to figure out which is the limiting reactant. So I'm going to reread this question before I answer this. As you can tell, I haven't gone over this yet. To figure out which is the limiting reactant and which is the excess reactant, we need to know how much sodium chloride each reactant can produce. Oh. Awesome. 1 chemical will limit your reaction, other will be left over. Okay, yeah. So clearly, the 14 grams of sodium, or Na, is limiting us a little bit. Or actually, yeah, I think so. So this is where I got a little bit off. The theoretical yield shows us the limiting reactant. I wouldn't have been able to get that right away without a cheat sheet or something, but that's what goes there. So yeah, the theoretical yield shows us the limiting reactant. And so again, which is the limiting reactant? That's going to be our sodium. Okay. And which is the excess? That's going to be the gas. Okay. Makes sense. Okay. So I've been trying to formulate so you can kind of see where my brain's at and the possible confusion that I had answering that clearly. So I'm glad to show you where my brain ticks, but that's the basis of limiting reaction. So to summarize all of this information, you're given something and you're given a recipe. It's got to be kind of a recipe that makes some sort of sense in order to know what the limit really is. So meaning if again we use the eggs and flour, if I gave you 3 eggs and a bag of flour and I said this makes 1 bread, and you said okay, and then we proved it somehow, okay fine, it makes 1 bread. Well, now I give you 2 eggs and a bag of flour. You're not able to make the full 100% bread. You now can only make 2/3 of that bread. I hope these analogies make some sense, and congrats on understanding the sheet. Have a good day.